Swayam Prabha. Digital India. Educated India.
In this particular lecture, we are going to cover some of the key concepts of statics, which constitutes some of the initial chapters of engineering mechanics that you have studied. Now, if you remember, in some of those chapters, what we essentially tried to do is that we were given an engineering system, maybe a bridge or a building, or even a problem such as where you have a truck, carrying something with a rope. What we essentially did was that we idealized that particular system. We drew the free body diagrams, right, of the different kinds of forces which are acting, how to best approximate those forces. We applied the equations of equilibrium and we find the reactive forces. Now remember, all of civil engineering is essentially trying to replicate what is happening in reality. So you have a real life problem, and we are trying to idealize this to the best of our abilities using toy examples such as beams and columns and trusses and so on and so forth, such that we can apply our mathematical principles, our mathematical equations to these idealized structures. We find the stresses, the deformations, the strains and so on, and we hope that the real structure experiences similar kind of stresses, force and deformation. And that is why it is extremely important to have good idealizations of the real life problems that are there, right? And what do we mean by real life problems? For example, and so as I was saying, that these are the four principles of statics: the idealize, free body diagram, apply the equations of equilibrium, and find the reactive forces, right? Now some real life examples is that I'm not sure if you're familiar with this particular structure. This is one of the oldest structures which is known to mankind, where we have these particular, where we have this is a Stonehenge that you are looking at, right? So this is one of the oldest structures known to mankind, which is in England, right? Now how would you idealize this particular beam, maybe, right? So how I would idealize is that I will probably simply just draw a straight line and apply some support conditions at the two ends, right? Now this particular beam has some weight of its own, a self weight, so maybe an idealization of that one is a uniformly distributed load. And this is again an idealization. Remember, this particular stone that you see, it has different thickness at the different parts of it, maybe, so the load is probably not uniformly distributed, but as a approximation we can use that, right? How about this one? We have a truck over here which is carrying these logs of wood, as you can see, and what I can maybe idealize this simply as I have the left tires, which can be again maybe a roller. Here I also have a roller over here, and I have a uniformly distributed load on top, right? Now you can have, if someone is sitting on one of the logs, you can have a pointed load as well, but you get the idea, right? Now coming to civil engineering structures, this one, as you see, it looks like a cantilever. You have this building where you have the different units maybe sticking out of this particular building. So how do I idealize this particular system? I can simply have one particular end that is fixed, right? And this portion which is sticking out like this, I can have that as something like this. It has its own self weight, and inside these rooms there may be people, which may be these different point loads which are acting on this projected beam that is there, right? Some more examples. For example, if you take a look at this seesaw, I am sure several of you, when you were kids, you have probably done this seesaw, right? So what we have over here is that you have a beam, right? You have this particular beam that is there, and you have two people which are sitting over here, and the beam is supported by a fulcrum over here, about which you have this seesaw mechanism that is happening, right? So if you were to idealize this system, this is again simply a beam over here, and you have this particular fulcrum, right? And you have two loads of this boy and this girl who is sitting over here. And remember, now this thing to remain completely in the horizontal, the weight of these two members who are sitting on either side of this particular seesaw must be equal, right? We'll come back to this particular problem later. We'll see this problem again when we are studying about bending, but right now we're just focusing on some of the fundamental concepts of statics, right? Another example, if you are from a coastal city of India, or if you have been to Goa, or if you have been to Kerala or some of the other places, you must have seen the coconut trees there, right? So how do we idealize this particular system? This can be idealized simply like a cantilever. Again, you have a cantilever, right, which has a fixed end over here, and this cantilever has uniformly distributed load, which is the self weight of, acting vertically down, self weight of this the branch of the coconut tree, right? And also you have this entire canopy of leaves and the coconuts, which may be idealized as a point load acting at the very tip, right? Now, as a consequence of this, what would you have? You would have the support reactions, right, and you will have a moment as well, right? Now typically reactions are drawn with a cross. That's why I have crossed each of those arrows and the curved arrow for representing the moment that is over there, right? Now that once you have idealized the system, so what do we essentially do? We apply the equations of equilibrium, because at the end of the day we want to find what are these reactions which are over here, what are the magnitudes of these different reactions and the moments that are there, right? So we arrive at these equations of equilibrium. Now they can be written in different formats. For example, if you're writing in a vector format, it is simply your summation of the total forces acting on the system must be equals to 0, and the total moments, which can be represented as a product, the cross product rather, of the lever arms times the forces, that must be equals to 0, right? If you are dealing with a 2D system, you will have, suppose if you have a 2D system where your horizontal axis is x, vertical axis is y, you have the summation of the forces in the x direction must be equals to 0, summation of the forces in the y direction must be equals to 0. And remember, if you have a 2D system, for example, if I show you this particular one over here, I have the x-axis and I have the y-axis, so my moment must be coming about the z-axis over here. So I have the summation of mz equals to 0, right? Now if you have a 3D system, you have the x, y as well as the z-axis, then you have all the components of the forces and all the components of the moments that must be equals to 0, right? So you have summation of fx 0, summation of fy 0, summation of fz equals to 0, and similarly for the moment, summation of m of x must be 0, summation of m of y must be equals to 0, summation of m of z must be equals to 0, right? Now remember one thing, that these are actually sufficient to solve a problem only if it is statically determinate and stable. In this course, we look at some of the statically indeterminate problems as well. You will look at them more in some of the advanced courses that you will take in your later years. If you have a structure which is statically indeterminate, your equations of equilibrium are not sufficient. You need other conditions to find the reactions and so on. But for now, this is okay, right? So we did these, that you see, we idealize the system, right? We do the free body diagram essentially to replicate the real system in our in our idealized system, right? We applied the equations of equilibrium. Now what we do after that, we find the reaction forces. Now as I said, that it is extremely important to properly idealize the supports and the connections, because your results may vary wildly if you are mistaken in idealizing your supports and connections. So we will look at some of the common supports and connections which we use in our civil engineering systems, and how you can idealize them and what are the type of forces which are acting on them, right? So one of the first one is the roller support. Remember the roller support which you had drew on the tractor as well. So roller support essentially allows for the translation. For example, as you can see here, that you have a bridge where the beam of the bridge, also known as a girder over here, rests on this particular roller that is there, and it can be idealized as this one over here. So this does not allow, so it is probably it does not allow the vertical movement, but it allows the movement along this translational axis. So it you have these rollers, so it is free to move along the horizontal axis. Another example of that may be a roller like this, also from a bridge. It looks a bit risky, but probably a lot of calculations has gone behind developing such a slim kind of a bearing. This is also called a bridge bearing that you have. It's called a roller kind of a bearing, right? Now any idea why these rollers are provided? Essentially, if you think about it, the bridges are typically subjected to, during the daytime, a lot of warmth from the sun, and if you are in cold regions, you may reach sub-zero temperatures at night as well. So your structures tend to expand and contract, right? So if you have your beam at one point, one end is fixed, the other one you put maybe a roller, so that this thing can expand and contract, and the roller sort of accommodates this expansion and contraction. If you are making both the sides as pinned, right, then this particular member is trying to expand or contract, and if you don't allow that, you will start to develop some cracks or other kinds of problems in your girders, right? So this is the roller support. You can have a vertical roller as well, you can have an inclined roller. This is a 3D kind of a roller over here, right? You can have a pinned support, which I was saying as one of the end is pinned. Now remember, if I have a pinned support over here, it allows this kind of movement. So it allows some kind of a rotation, right? But it does not allow, if I'm pulling it, right, it does not allow translation along the x-axis. If I'm pulling it vertically up, it does not allow translation about the y-axis. Now remember, this is extremely important, that in the principles of statics, if you are not allowing a particular deformation or a rotation, you will consequently develop a reaction force or a reaction moment, right? For example, as you can see here as well, I will repeat this one more time. You are not allowing translation about here, so you feel a pull in your particular support. You are not allowing a translation, so you have this particular reaction over here, right? You are not allowing a translation about the vertical direction, so you have this particular reaction as well, right? So this is again a 2D example where you have the pin slightly inclined, and here you have this particular kind of a 3D kind of a pin. The best way to understand this is maybe with your ball and socket joint over here. You can literally move your arm anywhere, but it doesn't it has these reactive forces. It doesn't, because it does not allow it to pop out, right? So it allows the movement, right, but it develops the reactive forces. When you are suppose pulling this particular arm, you will feel the reaction coming over to your shoulder, right? Now moving on, we have the clamped supports. So as I said, the cantilever example, remember, as you see in this particular beam as well, you have these pins over here. Now again, just backtracking to what I said, if you are not allowing a particular translation or a rotation, you will develop those reactions. So if I have, in contrast to my pin example, if I now clamp it completely, I am not allowing this x-axis movement, I am not allowing the y-axis movement. In addition to that, I am not allowing any moment. Remember, this particular beam, it deforms, it will undergo if I clamp it, and if I try to bend it, you will see some deflected shape of this particular beam. But here at this particular point, I essentially have no rotation because I've completely clamped it. Now since I am not allowing any rotation, what will I develop? I will develop a consequent moment. Remember, here I had restricted the movement around this direction, so I am developing a reaction. I am restricting the rotation also, so I will develop a moment. So essentially, to restrict the translations, I have Rx and Ry, and also I have a restricted particular moment as well, right? You can have a 3D kind of a clamp support as well, similar to the 3D pinned or the 3D roller support, right? You can have a sliding support where it is it's kind of a fixed connection, but if you allow vertical moving up and down over here, so that is idealized using these rollers. You can have other kinds of fancy supports like the elastic support or the spring support. These are kind of prevalent in nuclear power plants, where you have equipments which are resting on this spring support. So when in an earthquake or something happens, that you are not rigidly connected and you don't get damaged, you have maybe some leeway to move around, right? You can have rotational springs as well, which allow for some amount of rotation. It is not completely clamped, so maybe it is loosely clamped. So loosely clamped, you have some kind of flexibility which is going to allow some kind of rotation about this particular point over here, right? Now you can have a pin connection. Now remember, this pin connection is different than a pin connection, right? The pin connection, for example, if you take a look at this beam over here and over at this particular point, you have the pin connections over here, whereas this is an internal pin. This is what I mean by a pinned connection. So maybe I will write it over here. So this is an internal pin or hinge, right? So what it essentially does, and the best way to understand is that if you have a laptop, the hinge of the laptop, or if I have to show you, for example, in my notebook over here, right? If you idealize it, so this is, if you have your laptop, this is where your keys are, and this is your monitor, right? So it allows for this kind of movement, right? If you take a look at the beam again, see, if this one will allow this kind of movement over here, but if I try to pull it, I cannot. If I try to, you know, pull it vertically up, I cannot as well, but I can always make it rotate about this particular hinge. So this is a kind of an internal hinge connection that you have, right? So this is a pinned connection, right? Now that we have all these different kinds of support conditions, we have the idealization of a particular structure, what do we do with it? We find the support reactions. That's our objective. At least that was our objective till we studied statics. For example, if you take a look at this particular frame that is there, which has the, you know, different kinds of loadings. You have a triangular load over here, you have a uniformly distributed load vertically down, you have a uniformly distributed load acting about the x-axis, right? And as you can tell that you have a pin connection here at D, you have a pin connection here at A as well. So essentially, how will I find what are the reaction forces coming at D and what are the reaction forces coming at A? First, I will probably, and you would too, if you were solving this problem, you will try to make your life easier. You will probably sort of idealize this triangular load, which is over here, as simply maybe, you know, an idealized load over here as an equivalent load. Now, since it's a triangle, what would be the magnitude of that particular load? Suppose that represent the load as FQ naught. That will be the area of the triangle, that is half times base times the altitude. So that is going to be half times my base. The length of my base is C over here. So half times C times Q naught, right? So this is the altitude over here. So that is going to be the total load FQ naught. Similarly, you can have an idealized load over here, that is your FQ2. Similarly, you can have an idealized load over here, that may be your FQ1 over here, right? Something. So when after you idealize the loads, you can maybe blow out your beam and your frame to calculate the support reactions at these particular points D and this particular point A over here, right? Something similar to this. So as I was showing, this is the equivalent load, that FQ naught, which is half times this particular length times this particular height. Then you have the equivalent load FQ2 over here, and lastly the FQ1, and you have sort of segregated. Remember, the whole system is in equilibrium, so the individual parts must also be in equilibrium. So you have separated the top beam, the inclined beam over here, and remember, here you're calculating the reactions dx and dy. Now, since this was connected to over here, you must transmit the equal and opposite forces. So you have a vertical dy and the horizontal dx over here, equal and opposite, because remember, the point D, if I just have to go back, this point was not going anywhere, it was just staying over there. So that means if I sort of segregate that, the forces must balance out for that point to stay at the same time. So if I just separate this element and take these loads and these reactions, whatever I calculate must be equal and opposite to what I get over here, right? And you can calculate the reactions, what you're getting at this particular point as well, right? So now that you have sort of understood that what we are essentially trying to do with these principles of statics, you calculate the reactions and so on. So what are these principles which we are going to take, and what are we going to do with it in solid mechanics? Now I'll just explain you through an example. For example, I'll take a very simple case where I have this particular piece of sponge that is there. So suppose I'm just holding it, maybe a clamp kind of a fixed support over here, right? And I'm applying a particular point load over here, maybe using this one. I apply a particular point load, right? So what do you think I will feel in this hand? Since I'm pushing this over here, I will, you know, of course have to push by an equal amount over here. So I will have equal and opposite forces which are acting over here. Now, because of this particular force, I am developing another force P over here. If this magnitude is P, I will develop another force P over here, right? So this is up to which we had learned when we were discussing statics, right? You have if you have to idealize this, again, let's just run down the steps. You take the structure, you idealize it, probably you will idealize as a beam, right? My hand, you will probably idealize as a fixed support over here, and this pen with which I'm applying the force, I probably idealize as a point load, right? So you have the beam a fixed end, a point load, all you will do is that you will calculate the reaction. Now I can make this problem, increasingly complex by adding other kinds of, forces, but I'm not. I'm just, concentrating on one particular direction over here, right? Now I want you to watch closely. Now if I have this particular beam over here, now see what happens as I keep on pushing it. As I keep on pushing it, do you see the vertical lines which are drawn over here as well as the horizontal lines, especially the vertical lines, they start coming close to each other, right? Now why does this happen? This happens because this particular beam now has some internal forces, right, which is causing this internal deformation. The overall deformation that you see, if I have to sort of dramatize this one, if I am just pushing it, right, the overall deformation that you see in this particular piece of sponge is actually an aggregation of the individual deformations, right? This is the main focus of our course on solid mechanics, right? We try to find these internal deformations, the internal forces, the internal stresses which are going on in our structure, right? So the objective of this course, that once you're done with your fundamental principles of statics over here, the idealizing, applying the equations of equilibrium and so on, what we try to do is find some of these internal forces, the internal deformations, the internal stresses. From your +2 curriculum, you probably know the what are stresses is the force divided by the area. We look at several other kinds of stresses in the solid mechanics, but essentially what we're trying to find is that given a body, a deformable body, which is subjected to maybe a multitude of forces in addition to the axial, you have the bending forces and so on, what is the internal deformation, internal stresses, internal strains which are going on, which is a step above what you had learned in the solid mechanics course, right? So again, just going back to this particular example, what we are trying to do again is that we are trying to find these internal forces, these internal shear forces, internal moments which are acting in your structure, to find the internal deformations of the frame. Until now, when you had studied statics, you were just focused on calculating the reactions and we were done with it. But now we are trying to find what is going on in the inside of the body, how much is the body going to deform, what are the kind of stresses the body is particularly subjected to, right? So with that being said, I would like to conclude this particular lecture. In the next lecture, we will move on to the core of our course. We will look at some of the concept of stresses and strains and some of the other related concepts as we go ahead in this particular course. All right, I will see you guys very soon. Please watch this lecture and learn from it. Thank you.